Section 9.4, Comparison of Series. So far, to determine the convergence or divergence of a series, the terms of the series had to be fairly simple, and the series had to possess special characteristics for the convergence test to be applied. A slight deviation from these special characteristics can make a test non-applicable. Now we will study two additional tests for positive term series, which allow us to compare a series having complicated terms with a simpler series whose convergence or divergence is known. So first I want you to take each of these pairs of series and look at them on your calculator and compare them. Take a few minutes to do that. I'll wait. For the first one, we notice that this is a p-series with p greater than 1, and so we know it is going to converge. Next thing we know is this series, 1 over n cubed plus 1, as n gets larger, the denominator gets larger, but the fraction gets smaller. Since we know this converges and this one is smaller than this one, we know it also converges. So here we have a geometric series with r being 1/3. The absolute value of r is less than 1, so our geometric series, 1 over 3 to the n, converges. What do we know about this one? You should have seen it converged. Notice that 1 over 3 to the n plus 2, it term by term is smaller than 1 over 3 to the n is. For number 3, we have 1 over the square root of n, which is 1 over n to the 1/2. This is a p-series where p is a half, which is less than 1, so we know that it diverges. Let's look at what we're comparing. 1 over the square root of n minus 1. Term by term, this fraction is bigger than this one. And since we know this one diverges, and term by term, each term of this series is bigger than each term of this series, we must conclude that this series also diverges. Let's remember, as a denominator gets smaller, compare the fourth term. I would have the square root of 4, which is 2. Here I would have the square root of 4, which is 2 minus 1. Okay? The smaller the denominator, the bigger the fraction. So term by term, this series, term by term, each term is larger than this one. We know this one diverges, so this one diverges. And that brings up our direct comparison test. If I have a series, b sub n, and it converges, and I have another series, a sub n, which is less than or equal to b sub n, term by term, then a sub n has to converge. If I have a series, b sub n, and it diverges, and I have another series to compare it with, which is term by term bigger than b sub n, then that series, a sub n, also diverges. So we can say a less than a convergent series converges, a greater than a divergent series diverges. Now, as a note, this is for a memory. You may not use this as a reason in your work, but it is something to help you keep the rules straight. In using the direct comparison test, you will usually compare the series you're interested in to a p-series or a geometric series unless you are told to compare it to another series. So here's the series we want to look at, number 4. The series as n goes from 1 to infinity of 1 over n cubed plus 1. Now, we want to compare it to 1 over n cubed. Now, what do we know about 1 over n cubed? This is how you state this. We're going to state what we're going to compare it to and state what we know about the one we're comparing it to. We know 1 over n cubed is a p-series with p equal to 3, which is greater than 1, and so this series converges. So now what we have to show, our known series converges, we have to show that the series we're interested in is less than our known series. So we have to state that 1 over n cubed plus 1 is less than 1 over n cubed. So the series, n goes from 1 to infinity of 1 over n cubed plus 1, converges by the direct comparison test. Now here's a question to ponder. What if this had been an n cubed minus 1? We could not compare it to n cubed because n cubed 1 over n cubed minus 1, term by term, would be greater than our known series, and greater than a convergent series does not tell us anything. Number 5, 1 over 3 to the n plus 2. Let's compare it to 1 over 3 to the n. We know this is a geometric series with the absolute value of r equal to 1/3, which is less than 1, and it converges. So now we have to show this one is less than this one, which we know to be true. As the denominator gets bigger, the value of the fraction is smaller. So term by term, this series will have terms that are smaller than this series. So we know this series converges, so by the direct comparison test, this series converges. Okay, I can see that term by term, this is going to be probably bigger than the one I want to use, and so we're going to compare it to 1 over n to the 1/2, which we know is a p-series where p is 1/2, which is less than 1, and it diverges. Well, term by term, this series is greater than this one, so since we know 1 over the square root of n diverges, then 1 over the square root of n minus 3 also diverges by the direct comparison test. What if that denominator had said square root of n plus 3? Again, less than a diverging series does not tell you anything. And so this is why we have a reason for our next test. Pause the video and write down these examples. Often, a series closely resembles a p-series or a geometric series, but you cannot determine the term-by-term comparison necessary to apply the direct comparison test. So we can use a second comparison test, and we call that the limit comparison test. This works well for comparing messy algebraic series to a p-series. Here's the test. Suppose we have two series, both are positive terms, and the limit as n goes to infinity of a sub n over b sub n is L, where L is both finite and positive. Then our two series either both converge or both diverge. So what we know is we know that one of them is going to converge or diverge, and so if I get a finite positive number, if one of them converges, the other converges. If one of them diverges, the other diverges. Take a moment with these 4 examples and make a suggestion to yourself of which series you might compare them to. Take a couple of minutes, I'll wait. All right, a p-series with which we could compare for number 7 would be obviously 1 over n squared. We obviously cannot do a direct comparison. There's too much going on here, but we could do a limit comparison. What about this one? Compare it to 1 over the square root of n. This one, that's interesting. N squared on top, n to the 5th on bottom. We're going to compare it to 1 over n cubed. And this one here, we have n to the 1/2 on top, n to the 3/2 on bottom. So we're going to compare it to 1 over n. Now here's the things we know. This is a p-series that converges. So if we get a finite positive limit, then this one's going to converge. This is a p-series that diverges, with p being 1/2. So if we got a positive finite limit, then this will diverge. This is a p-series where p is 3 that converges. So if we get a finite positive number when we do the limit, this one will converge. And this is our harmonic series, which we know diverges. So if we get a finite positive number, this one will diverge. We're going to start with our first problem that we had up there. What we want to do is state which series we're comparing it to and what the properties of that series are. Okay. Now we're going to take our limit. It honestly doesn't matter if you do the one we're interested in over the one that we know. I can do it the other way. I should still get a finite positive number if I get it in one direction with this over this. I would certainly get it with this over this. It would just be the reciprocal limit. So when I go to look at this, 1 over 3n squared minus 4n plus 5 over 1 over n squared actually becomes n squared over 3n squared minus 4n plus 5. We know our horizontal asymptote exponent rules. The degrees are the same, so the limit is the ratio of the leading coefficient. Notice what we have here. That number is finite and positive. So we know this one converges. We got a finite positive limit, so this one converges by the limit comparison test. Example 12, which was actually number 9 up at the top of the page. We're going to compare this to 1 over n cubed, which is a p-series where p is 3, which is greater than 1, and it converges. So here we go. The limit of the series we're interested in over the series we know. Simplifying our work, notice that n squared minus 10 over 4n to the 5th plus n cubed minus 2 divided by 1 over n cubed brings that n cubed as a coefficient on the top of the fraction. And we can see that our degree of the top is 5, our degree of the bottom is 5, so our limit is 1/4, which is finite and positive. Therefore, this series converges by the limit comparison test. Pause the video and write down these examples. All right, let's look at this series. Looks like we're going to compare it to 1 over n cubed, which is a p-series where p is 3, which is greater than 1, so this converges. Now, let's look at this. Notice that we have to use the limit comparison test because 1 over n cubed minus 2 is not less than 1 over n cubed. This is why we cannot use direct comparison test. We know that 1 over n cubed converges, and if term by term the series we were interested in had smaller terms than the one that converges, we would be able to state that this series converged by direct comparison test. But term by term, each term of this series is greater than each term of this series. Now we know this one converges, so let's look at what happens when we go to find our limit. Oh, I get a limit that is still finite and positive, so guess what? This series converges by the limit comparison test. Isn't that nice? All right, problem number 14, which was number 8 on the previous page. We are going to compare 1 over the square root of 3n minus 2 to 1 over n to the 1/2, where our p is 1/2, which is less than 1, and we know this series diverges. So here is our limit we're going to do. Now, this brings up, how do I simplify this? Okay, so we know that, first of all, we can do this. But how am I going to work with the simplification here? We have to go back to early in the course when we had something like this. We needed to divide every term by the highest degree term of what is under the radical. Under the radical is n to the first power, so I'm going to divide 3n over n minus 2 over n, and I'm going to have to do it under the radical on the top. This is going to give us the limit as n goes to infinity of 1 on top over 3 minus 2 over n under the radical. Okay, that gives us 1 over the square root of 3, which is finite and positive. Now, another way to do this problem is to recognize that we have n to the 1/2 and 3n minus 2 to the 1/2, and notice that this would go to infinity, and this would go to infinity, and so L'Hopital's rule could be applied. So we could do it that way. Either way, I have a finite positive answer. So since we know this one diverges, we know this one diverges by the limit comparison test. Notice you have to state what your test is you're using. Pause the video and write down these examples. Let's look at number 15, which was number 10 on the previous page. Remember, we were going to compare it to 1 over n to the 3/2, which is a p-series with p equal to 3/2, which is greater than 1, so we know it converges. So let's look at our function. We are going to do all kinds of simplifying. This is n to the 1/2 over n squared plus 1 divided by 1 over n to the 3/2 means times n to the 3/2. We get n squared on top over n squared plus 1. And that limit is 1, which is finite and positive. So this series converges by the limit comparison test. And now we get a really interesting one. Notice on top I have a polynomial times an exponential function. What are we going to compare it to? We are going to compare it to 2 to the n over n squared. Now, what we know is 2 to the n gets bigger much faster than n squared does. So we're looking at the limit of 2 to the n over n squared, which is not 0. So this series diverges by the nth term test for divergence. All right, here we go. We are going to compare our series we're interested in to this known series. When I do the necessary algebra, we get this, and simplify, I get 1/4, which is finite and positive. So since we know this one diverges, we know the one we're interested in diverges by the limit comparison test. Pause the video and write down these examples. Your TPs are 3, 7, 15, and 17.